Hey everyone, today we're here to talk about switches, what they do, what layer of the OSI model they live at, and why they're so important to network performance and security. Now switches connect devices within the same local network together, and they primarily operate at layer 2 of the OSI model, the data link layer. So how does a switch work? Every network-enabled device has a unique physical address called a MAC address. When a device sends data into a switch, the switch reads the destination MAC address, checks its MAC address table, and forwards the data to the correct port. Instead of sending traffic to every single device on the network, the switch forwards the data only to the correct port. This essentially improves efficiency, reduces unnecessary traffic on the network, and allows for many devices to communicate on the network at the same time. In order to get data to the correct port, the switch maintains what's known as a MAC address table, and as devices communicate, it learns which MAC address exists on the physical port, and it updates its MAC address table dynamically. This is what allows for internal device-to-device communication in offices, in data centers, and in enterprise environments. Here's where this becomes important from a security standpoint. Switches operate at layer 2 in the OSI model, but in network design, they're typically placed at the access layer, the part of the network where an end device connects. This means they're often the first infrastructure device laptops, servers, printers, and IoT systems attached to. Unlike routers or firewalls, switches are rarely exposed directly to the internet. Attackers typically interact with switching infrastructure only after gaining an initial foothold through phishing, compromised credentials, or vulnerable internal systems. Another thing that's important to know is that physical access is not always required in order to exploit a switch. While plugging into an unsecure port is one risk, many switch-related attacks occur after an attacker has already gained internal access to the network. Once a malicious actor or a pen tester is inside the network, the next step is local discovery. So they're identifying nearby devices and they're mapping how those devices are communicating with each other. For example, ARP spoofing can trick devices into sending their traffic through the attacker's system instead of directly to intended destination. This allows attackers to intercept, observe, or even modify communication between systems. Another form of attack is MAC flooding, which is an attempt to overwhelm the switch's MAC address table. If the table is overwhelmed, the switch behaves more like a hub, broadcasting that network traffic out more broadly, and that essentially gives the pen tester or the attacker more visibility into network communications. If the attacker or pen tester already has access, they don't need to break that network parameter again. This is a form of exploiting the internal trust relationships and switching behavior in order to expand access and move laterally across the network once they're already inside. So modern switches also support VLANs, which allows administrators to logically segment networks even if they share the same physical switch. This essentially restricts what systems are allowed to communicate. Keep in mind that segmentation only works when it's configured properly. Misconfigured assignments or over-permissive trunk ports can allow for communication between networks that were meant to remain isolated. That's all I have for you guys today on switches. Make sure you follow along for the next video. We'll be building on this and discussing wireless access points and how wireless access points integrate into switch networks while still enforcing segmentation and security controls.